focused? Hang on a sec. Okay. Did everyone get the notes for today? Okay, so trees actually are, has a fairly simple definition. So a graph with no cycles is acyclic, okay? And a forest is an acyclic graph, and a tree is just a connected acyclic graph. Okay? So in other words, a tree is just connected but plus no cycles, right? Connected plus no cycles. So acyclic. Okay. So for example, here's an example of a tree. Okay. So the vertices, everything is connected, right? There's a UV walk from every vertex to every other vertex, and there's no cycles in this graph. So this is an example of a tree. And if you have a bunch of trees, well, then you get a forest. Okay. So this would be a forest. So in other words, so a forest is just, there's no cycles in the graph, but you're not requiring the thing be connected. Right? Now, in terms of applications, actually, it's kind of interesting if you look at the history of this. Graph theory in general was created to actually solve some applied problems. So one of the first examples of trees was from Kirchhoff voltage laws. Have you guys ever heard of that before? Like maybe in a physics class or something like that. And another place that this came up was in chemistry. Okay, so actually Arthur Cayley was studying the different types of trees that could come about from molecular composition. So some molecules that you want to build will take the form of a tree. Okay, so what's a leaf? So a leaf, or sometimes we'll call this a pendant vertex, is just a vertex of degree 1. Right? So for example, on a tree, well, it doesn't, in order to have a leaf or a pendant vertex, you don't actually have to have a tree. You could just call something off of an arbitrary graph that's a degree 1 vertex. You could still call it a leaf. But usually we're using this terminology when we're talking about trees. So for example, this right here would be a leaf, right? Because the degree of this vertex is 1. And there are several leaves, right? So one interesting question might be, okay, is there a minimum or maximum number of leaves that you could have for a graph? That's something you could ask, or a tree specifically. And then you could think about the more general situation of a forest. Okay? All this terminology is somewhat makes sense, right? Trees, leaves, forests, right? Okay. Now, every edge of a tree is a cut edge or a bridge. Do you remember why that would be? So do you remember a cut edge is one where if you remove it, it will increase the number of connected components in the graph, the number of components. So for example, if I removed this edge, then I would get, let me just show you real quick. Okay. So let's say that I have, here's a tree, right? Acyclic and connected. And let's say that I remove this edge. What would I get? It looked like this, right? Do you agree that the number of components for this guy is greater than the number of components for this one, right? Now, why is that? That every edge of a tree is always going to do that. Do you remember that we actually had a classification theorem for cut edges, which is an edge is a cut edge as long as it's not on a cycle. Remember that? So if you're in a tree, there are no cycles, right? So that means every edge does not belong to a cycle. Does that kind of make sense? Now, another name for a cut edge, I should have mentioned this before, is a bridge, because a bridge is kind of like, a bridge is like an essential connection from point A to point B, right? There may be other bridges in real life, right? But in terms of, if you just have this like small localized graph, you think of a bridge as like essentially connecting these components together. Okay. We're okay with that? So every edge of a tree is a cut edge. In other words, sort of it's essential to the connectivity of that graph. Okay. And if every edge of a connected graph T is a cut edge, then it turns out that that must be a tree. Okay. So if every edge is essential to the connectivity, in which if you did remove it and you did increase the number of components, then it turns out that you must be a tree. Okay. Now think about why that would be. In order for you to get a tree, what do you need? You need it to be connected and no cycles, right? Well, if every edge is a cut edge, then you automatically would know that there are no cycles. So the last part that you would just need is to verify that it would have to be connected. But if every edge of a connected graph, I'm telling you it's connected, right? So do you see that you're getting the two ingredients to a tree? It's definitely going to be acyclic. Okay. Okay, next, if T is a tree, then for every vertex V in the tree, T minus delete V is going to be a forest with exactly the degree of V components. So that's how many connected components you would get. So in order to get you to agree with this, let's just do an example. So let's say that I have this graph. Okay, and here's V. Now what's going to happen when I delete V? Remember when you delete a vertex, you have to delete the incident edges with that vertex as well. So you can kind of draw this little dotted circle around it to remind yourself that you're going to actually have to remove those edges as well. So if I delete V from T, it'll actually look like this, right? I'll have this piece and I will no longer have this edge, and I will no longer have this edge, but I'll have that isolated vertex down here. I'll no longer have this edge, but I'll have this little piece over here. See that? And now how many components do you get? Well, it's equal to the number of edges that you had to remove, and you had to remove one edge for every one that's incident to V. In other words, the degree of V. So do you see that you're going to get exactly that many components, whatever the degree of V was? Now, notice what would happen. Now, let me ask you this. Is this telling you that you will always get a disconnected graph? Is that saying if you remove any vertex, you will always increase the number of components? Is that what that's saying? No, right? Because what happens, do you see that, what if the degree of V was 1? Then how many components do you get with T minus V? If the degree is 1, then you'll have, this is 1 component, right? So in other words, this is actually saying if you were to delete a leaf, it should still be connected. You see that? And indeed, if you deleted, say, this vertex here, the rest of this would still be connected, right? And you'd have exactly 1 component, which is the degree of that. Okay. So just be a little careful that this only applies to trees as well. It's not a general thing on arbitrary graphs, okay? But if you are a tree, then if you were to delete some arbitrary vertex, you'll get the degree of V components. Right? Now that does not mean that it's always going to increase. The degree doesn't necessarily have to be 2 or more, okay? Because you could have leaves. Okay, now we're starting to classify some properties of this tree. Okay, so every non-leaf of the tree is a cut vertex, like in the previous example. So do you all agree that when I removed V, it definitely increased the number of components, right? In other words, it was a cut vertex. That vertex is sort of essential to the connectivity of, say, connecting the vertices over here to over here. Do you remember the original definition or the classification was that a vertex is a cut vertex if you can find 2 other vertices in the graph such that every path that goes from one vertex to the other contains that vertex. So it's sort of essential to the connection between those 2. So for example, if I took these 2 vertices, do you see every path that connects those 2 contains V? So if I were to remove V, I no longer will have a path connecting these, right? So that's why this is a cut vertex. The original definition is just if you delete it and you increase the number of components. But from what we're saying up here, as long as you're not a leaf, then the degree will be bigger than 1, right? If you are a leaf, the degree is 1, so it'll stay connected. But if you're a non-leaf, the degree is bigger than 1, which means that you will increase the number of components. You see that? So it'll be a cut vertex. Kind of interesting. All right. So trees are special, that you can kind of get a handle on the structure a little bit more from, well, it's highly specialized. I mean, you have to be connected and have no cycles. Okay. But the nice thing about trees is the more that we know about trees, they can help you do a lot of other things on a general graph. Okay. Like, for example, you can think of a tree as sort of the skeleton of a graph that might have more connection. Okay. So maybe you can prove some things on trees that then can be used for arbitrary graphs. Okay. Now, all trees and forests are bipartite. Could you guys prove that? I claim that you could prove that by referencing one theorem that we already have. So in order to be bipartite, what do you need to prove? The original definition says you got to find a bipartition of the vertex set. So all the edges go from one partite set to the other one. But we had a theorem that said, Yep, Koenig's theorem, right? So Koenig's theorem, that one says you're bipartite if and only if you have no odd cycles, right? But if you're in a tree, you have no cycles at all. So you definitely don't have odd cycles, right? So by Koenig's theorem, since trees have no cycles, in other words, they're acyclic, trees definitely have no odd cycles. So trees are bipartite. Well, that's nice. Now we have some structural classification of trees that could be interesting. Okay. Paths are trees. Well, could you prove that? I mean, the path graph in general, the way that it's defined, it's connected and there's no cycles, so it's definitely a tree. Okay. A tree is a path if and only if the maximum degree is actually equal to 2. So that's kind of interesting. All right. So connected and acyclic with max degree equals to 2, you could prove that it's a path. And if you're a path, well, that direction's easy, right? That the max degree is 2. That's just from definition. Okay, the center of a tree is a vertex or an edge. We defined what the center of the graph was, right? Before, when we talked about the eccentricities. Should have been in that note set. We didn't talk about that? So if you take, so do you remember the, the radius is what? The minimum eccentricity in the graph, right? Is that the definition? And the diameter was the maximum eccentricity. If you take all the vertices that have minimum eccentricity, and then you look at the spanning subgraph that those things generate, you call it the center of the graph. It's sort of like the core of the thing. All right, maybe I'll give you an example. How about that, okay? So the center of a tree is a vertex or an edge, and its incident vertices. And its incident vertices. I mean, you can't have an edge by itself without some incident vertices. But let's just look at an example. So K14, for example, would look like this, right? So K14 is a tree. Okay. And it's bipartite, right? The core, the center of this won't really be that interesting because what are the eccentricities? 2, 2, 2, 2, and 1, right? So the center will be, so if you draw all the vertices with minimum eccentricity and you take their spanning subgraph, you're just going to get this isolated vertex. So this would be the center. Okay, what about this graph? So let's draw another tree that's not K14 here. Okay, what would the eccentricities for this be? So this vertex is distance 3 away from this one over here, right? What about this one? 1, 2. So 2, 2, 2, 2. So this is wait, is this? Oh, 3. That one's 3. And then this one's 3, right? And then of course this one has to be 3 by symmetry, being 3 from over here. Now this vertex is distance 2 away from that one. And this one is distance 2 away from these ones. So do you agree that those are the eccentricities? Okay. Now the center, all you do is every vertex with minimum eccentricity, you put these down, and then you look at what is the subgraph that's generated from those. Okay. So what did we call that? So a spanning subgraph has to contain all the vertices, right? But then we had a name for once you create a vertex set, you're going to add in all the edges that happen to be connecting, that are present within these. So for example, I'm going to add in this edge because it's part of this. These vertices essentially will span or generate the missing edge there. Okay. The induced subgraph. Sorry, I was trying to think of what it was. That caffeine took a little while to get to my brain. Okay, the induced, right? It's vertex induced from these two. Okay, so all that the induced just means you give me the vertices, and then you're going to add in all the edges that are present with those given vertices. So do you agree that this is the one that's present? So this would be the center of this tree. And so just looking at these two examples, the center of a tree is going to either be a vertex or it'll be an edge. And by saying it's an edge, I also mean the two incident vertices that will be on the end there. So any tree, that'll actually happen to, the center will always have to look like that actually. To be honest, that doesn't have the most amazing applications. It just is giving you another structural thing that could potentially be useful. Okay. But it is kind of telling you that you can't have these minimal eccentricities sort of spread out within the tree. It sort of has to have this central component to it. Okay. Okay, now what are some results? So using that definition and looking at these properties, what are some things that we could say? Well, one thing is that you might ask is, how many leaves can you have, or what is the minimum number of leaves that you could have in a graph? Right. So every tree with at least 2 vertices has to have at least 2 leaves. Okay. And then moreover, deleting a leaf from a tree on n vertices will produce a tree with n minus 1 vertices. So in other words, it'll still remain a tree. It'll be connected and acyclic, but it'll have n minus 1 vertices. Okay. So let's prove this. Okay. So the proof I thought would be good to see because you can use a technique that we haven't seen before. All right. So what we're going to do is we're going to pick a path that's a maximal path. Okay. So this is a very useful technique. So let P, and so I'll just define P using this alternating sequence of vertices and edges. So let's say it's U, E1, V1, E2, V2, E, L. So let's say we have L. And then let's go VL plus 1, and then we'll have, yeah, sure. I mean, it doesn't really matter. So let P be this alternating sequence of vertices and edges, and this will be a maximal path, be a maximal path. Okay, now what do we mean by that? So maximal path, we just mean that it's not properly contained in any other path. Okay, so visually, let me just give you an example, maybe up here. Okay, so let's say that I have U and V like this. Do you see that I could create a path from U to V that's maximal in the sense that there is no path that's bigger than this that contains it. There are paths that are that could be within this path, right? For example, if I just went from U to this vertex, there is a path that's contained within this red path. But by making the claim that it's a maximal path, I'm saying that there's no path that's bigger than it. Okay. We okay with that? So this is actually a very useful technique. Why can we assume such a thing actually exists, first of all? Well, there's actually not much that you have to assume to say that you can create a maximal path. Even if I gave you a graph and I didn't tell you that it was connected, there is a maximal path in there. It could just be length 0, right? It could just be isolated vertices. A maximal path could just be a really simple one, okay? But even if it had cycles or it was connected, yes or no, you can still make an assumption like this. So this is a very useful technique to kind of remember in general for this course. You can always assume that you have a maximal path, right? That's a very useful thing. Now, what can we do with this maximal path? Now, since P is maximal and the graph is acyclic and the graph is acyclic, the fact that it's acyclic, we can actually say another thing, which is that U and W are not adjacent, okay? U and W are not adjacent. In fact, even more generally, to any vertex on this path P. The reason for that is just this. If you happen to be creating a path and it was adjacent to one of these other vertices, like let's say W happened to be adjacent to one of these other ones, then you would actually have to have a cycle in that graph, okay? Because it would create a cycle somewhere. Do you guys kind of see that? Like for example, let's say, let me just show you what it could. So if you didn't have that acyclic condition, let's say that I had this. Okay, let's say I have this graph, okay? Do you agree that this red thing is a maximal path? Does everyone agree that the red is a maximal path? Because if I were to try to add in that extra edge there, it would no longer be a path, right? Because then I would be repeating this vertex. Are we okay with that? It would be a walk, but it wouldn't be a path, right? Now, it is maximal. Do you agree that there's no other path that's bigger than this one? Okay. Right. Now, if this is my W and this is my U, W is connected to one of the vertices in this path. You see this? So this would be like V1, V2, V3, V4. So W is actually adjacent to V2. But in order for that to happen, the only way that that could happen is if the graph it has a cycle in it. You see that? If the graph is acyclic, then it's impossible for you to have this adjacency. That's what I'm saying here. Okay. So do you agree with this assumption that since P is maximal and the graph is acyclic, then these two end vertices cannot possibly be adjacent to any other vertex on that path, because otherwise you would actually have to have a cycle in the graph, but we assume that the thing was acyclic because we're talking about a tree here. Okay. All right. All right. Now what can we do? So it's not adjacent to any other vertex on P. Thus, what can you tell me about the degree? Well, this is a maximal path, and U is not going to be adjacent to any other vertex in the graph, which means that the only thing that it was actually adjacent to was V1, which means the degree is 1. And what about W? Well, it would have to be the same, right? We said that it's not connected to any other thing. Now this is a maximal path. So if there was another connection out there, then it would have had to been included in this maximal path because you're talking about connecting U and W here, right? So if your path was not long enough to begin with, then you would just add in, but it still would not affect the fact that that degree would have to be 1. So are we okay with the first part that, okay, so thus, i.e., what is this telling you about U and W? They are leaves, right? U and W are leaves. U and W are leaves. So we've satisfied the initial condition that every tree with at least 2 vertices, U and W, right, has at least 2 leaves. Everyone okay with that? Smallest situation would be this tree, right? It's got to be connected and acyclic. Now this is a tree, this one, but it doesn't have 2 vertices to begin with, right? It's connected and acyclic, but doesn't have 2 vertices. So this doesn't apply. Clearly it does not have 2 leaves. But as soon as you have 2 vertices, the tree must have 2 leaves. Usually it will actually have many leaves, right? Like for example, this one has 4. Okay, can we prove the next condition? So moreover, deleting a leaf on the tree and vertices produces, it'll still remain a tree, but it'll have n minus 1 vertices. Could we prove that? What do you think we could do? Well, you could just kind of think about this structurally, right? So if you're, suppose, to prove like the second part of this, suppose W is a leaf of T, okay? So these are kind of like 2 separate proofs, right? Okay. Suppose W is a leaf of T. It happened to be a leaf when I was doing this argument up here as well, okay? Let T prime be the tree, and then you're going to delete that leaf, okay? So it'll actually look like this. So I'm going to have W. I will have an edge that W is connected to, okay? And then the rest of this is not a cycle. I'm just giving you the rest of the tree, right? So the original tree is everything, including this leaf, but I'm going to remove it, and then the remaining thing, the remaining graph, we'll call that T prime. Is that okay? So the picture would look something like this. Now, in your graph, it's not actually going to have a cycle. If you want to create like a cloud for this instead, that's fine. Just, would that make you feel better if it didn't have an actual cycle in it? We okay? All right. Now, what can we say? So since W is a leaf, W is not on any path connecting to other vertices of the original tree. Do you agree with that? If W was on a path that connected 2 other vertices, then it couldn't possibly be a leaf. You'd have to have that the degree is greater than 1, right? For example, it'd be a vertex like this one here. You see that it's on a path connecting 2 other vertices, or it'd be this vertex which has degree 4, but you wouldn't be a leaf. A leaf is kind of like you're at this terminal point, and then you're not going to have any other continuing path. That one will be on some other that's connecting 2 other vertices, on a path connecting 2 other vertices. So are we okay with this? So since W is a leaf, W is not on any path connecting 2 other vertices of the tree. Okay with that? Okay, now, thus, if U and V are vertices of the deleted graph, what can we say? Then the path connecting them in the tree, the original tree, will actually be the same as the one in T prime where we deleted W. is the same in T prime. Do you agree with that? I mean, we just said if W is a leaf, there cannot be two vertices in the tree where W is on any path connecting those, right? Therefore, if you give me two vertices in the deleted one, so two vertices over here, so wherever those two vertices are, then any path connecting them in the original tree has to be the same in T prime. We agree with that? Because W is not going to affect that. If I delete it, I'm still going to have a path connecting them. Okay, what does that tell you? If you pick any vertices in, that's a graph still, right? So some graph, pick any two vertices, there's a path connecting them. What does that tell you about the graph? Yeah, it's connected. So do you agree that T prime is connected? Okay, so we're done with that. So T prime is connected. Now, what am I trying to prove? I'm trying to prove T prime is actually a tree, right? But it'll have n minus 1 vertices. So I'm almost there, right? I'm connected, but what else do you need to prove? Acyclic, right? So it'll definitely have the right number of vertices. If I delete W, do you agree that I've removed one vertex, right? So it'll have the right number of vertices, but right now I only know that it's connected. How do I know that it's acyclic? Yeah, deleting the original tree is acyclic, right? T. So if I delete the vertex, am I adding cycles in? No, then it'll be acyclic, right? That's pretty much the argument. If the original tree is acyclic, deleting that vertex is not going to magically add cycles, so it'll still be acyclic. Okay. So deleting W does not add cycles, so therefore T prime is acyclic. And then these two things together will tell you that it's a tree. Now T prime is a tree on n minus 1 vertices. Right. By deleting W, you're just removing that one vertex. Okay, so not so bad. Okay. But I think that this is a useful proof for you guys to see, because one argument that is very, very useful is doing something like this, where you pick a maximal path. Is that very useful for you? And a lot of times, if you have some kind of inductive procedure that's going on, deleting vertices can help you. Here, we didn't actually have to do any induction, because when you're classifying if something's a tree, you actually only need to show those two things are satisfied, that it's connected and acyclic. However, it turns out that you could classify a tree using a numerical thing as well, which is the next thing that I wanted to show you here. We're not going to be able to prove the entire part, but we'll be able to show some things. Okay, so here's a characterization of trees. So let T be a graph on n vertices where n is greater than or equal to 1. Okay, then the following are equivalent. So you guys remember from your other classes what that means? It's just if you have one, then you have all the other ones, right? The following are equivalent. So once you have one, you have all the others. So if you wanted to prove this, you have to show a lot of if and only ifs, right? Yeah, that's one of the strategies. Okay. Yeah, I'll show you our strategy in general. But here's what this is saying. So all of these things are equivalent. So T is connected and has no cycles. Well, that right there is actually the original. This is the original definition. Original definition of a tree. So does everyone agree that, well, that is the definition, but now we're saying that the definition is going to be equivalent to these things, okay? B is saying, as soon as you know that you're connected and you know the number of edges is just n minus 1, then that's a tree, okay? So in other words, knowing this to get A kind of implies the acyclic condition. So we'll kind of talk about this. C is saying if you have the number of edges is n minus 1 and is acyclic, then that's equivalent, okay? And then finally, T has no loops, and for all pairs of vertices, this should be a U and a V, okay? So it should be a UV. So just change that E to a U. Okay. For all pairs of vertices U and V, T has exactly one UV path. Okay. So kind of let me kind of show you what we're getting at here. So a tree, as soon as you have any two of these, you'll have the other one. Okay. So trees are connected and they are acyclic. But it turns out that if you know that the number of edges is n minus 1, equivalently, that's just saying that the number of vertices is m plus 1, right? That's equivalent to this. Pretty much any two of these will imply the other, okay? So any two of these will imply the other property. And hence, the graph is a tree. Okay, so is that kind of interesting? The original one is saying if you're connected in acyclic, it's a tree, but I could have acyclic and this edge condition, that'll give me connectivity, so it's a tree. Or if I have this edge condition and connectivity, it'll imply acyclicity, if that's a word. No cycles. Okay. Let me at least outline the strategy. We're obviously not going to be able to prove all of this today, but in order to show all of these things are equivalent, these are all if and only ifs. Okay, so our strategy is A will imply B and C. Then we're going to prove B will imply A and C. And then we're going to show C implies A and B. And then finally, we'll do the if and only if for the D condition at the end. So that one will be an if and only if. So if I prove D is equivalent to A, then for these other parts here, we've proven A is equivalent to B and C and so on. So just going back here, it's kind of what we're doing is this. So we're going to show A implies these two. Then we're going to show B implies the other two, and then C implies these two. And then finally, we'll establish an if and only if with A and D, which will connect D with these other two. All right. So sometimes the strategy is you kind of do a cycle of arguments here, but I think it's actually going to be more useful for you to kind of see that these three are essentially, they're essential. These are the three that you're going to be using most of the time anyway. This fourth one is just kind of a free one that you get. Okay. And of course, what I just drew here does not even include the argument for D in it. It's just kind of, A, B, and C are kind of saying this. Any two of these implies the other. We okay with this strategy? Do you agree with the logic of this? If I do this proof outline, that I'll prove all of those things are equivalent, or am I missing any equivalence condition? You could actually draw a graph for this, right? It would actually be a complete digraph, symmetric digraph on those three, and then you'd have another whatever. Okay, so A implies B and C. So let's at least write out what are our assumptions and what are we showing? Okay. So suppose what? So A is saying you're connected and acyclic, right? So suppose T is connected and acyclic, no cycles. And so what are we showing? You're going to show, now look, in B and C, you see B, I'm assuming, in order to get B, I have to prove that I'm connected, but I have to show that the number of edges is n minus 1, right? And to get C from A, look, I have to show that I'm acyclic and the number of edges is n minus 1. So do you see, as soon as I have one of these, I have kind of half of B and C. We okay with this? So that's why I'm able to do these two simultaneously with each other. If I'm assuming that I'm connected and acyclic, then all I need is connected and the number of edges is this, or the number of edges this and an acyclic. So I already have half of B and half of C. Okay? That's the only missing condition, right? Okay. How do you do that? Well, anytime you're trying to prove something numerical, and it's indexed by positive integers. I guess you could say non-negative integers, or you could say indexed by integers in general. The procedure is usually an inductive procedure. Okay, so we're going to proceed by induction. Proceed by induction. And let's do, you can do induction on n or you can do m, right? So I'm actually going to do it on n. So if I'm doing it on n, then we're actually going to show n is m plus 1. It doesn't really matter, actually. You can do the induction on n and then just verify that this equation is true, but you can proceed by showing either of those. Okay, so what's the base case? Well, the base case is the minimal situation that I could possibly be in, which is n is equal to 1, right? Okay, so that would be your base case. So base case, n is equal to 1. What would that look like? That is an isolated vertex, okay? Do you agree that this has no edges? And what is m? M is equal to 0, and n minus 1 is equal to 1 minus 1, which is 0. So these are the same. That's pretty easy, right? Now you got to do the hard stuff, right? Now, so induction hypothesis. So induction hypothesis. So let's say, suppose the size, which is the number of edges, right? The size of every tree of order n minus 1. Now the n minus 1 here we're assuming is going to be greater than or equal to the base case, okay? Greater than or equal to 1, is n minus 2. Okay, remember the number of edges, right? Number of edges. So do you see, for the case of n minus 2, we're assuming that we actually have the assumption, what we're trying to prove, right? In the end, we're trying to prove m, the number of edges is one less, one fewer, right? So one fewer edge would mean that you have n minus 2 edges. We okay with that assumption? Okay, so we're kind of basically assuming what we want, but for this particular case, okay? Now consider T with n vertices, okay? So now consider T with n vertices. I really should write that on the next line, actually, right? So that's the induction hypothesis. So now consider T with n vertices. Okay, what can we say that's going to be useful for us? Well, you want to do an induction you want to use your induction hypothesis, right? So in other words, right now I'm a tree with n vertices, and I want to get to a tree with n minus 1 vertices. What are some nice ways that you could potentially do that? Yeah, vertex deletion, right? So if you can cleverly delete a vertex and guarantee you have a tree with n minus 1 vertices, then you can use the induction hypothesis, right? Because it's saying, suppose that you have a tree with n minus 1 vertices, then you'll have this many edges. Do we have a clever way of doing that that maybe we've already discussed? Right here, right? Every tree has, you're guaranteed it has 2 leaves. And we just said, if you were to delete that leaf, right? Deleting a leaf from a tree with n vertices produces a tree with n minus 1 vertices. Genius, right? So just use this lemma. Do you agree with this? And I'm guaranteed I have one, right? Because n is going to be, I guess I should be very careful to say that this is a strict right? Strictly greater than the base case, right? The base case of 1, this thing has no leaves, right? But now that you're assuming you're bigger than the base case, then you're okay. We okay? We have at least 2 vertices, so we have 2 leaves. Therefore, we can guarantee we have a leaf. And if I delete one of those leaves, I will be a tree with n minus 1 vertices. So that's the key to using the rest of this. Okay, so consider this. So by the lemma above, we're out of time. So we'll pick up from here on, is it Wednesday today? Friday? Okay. See if you can finish the argument though. You're basically done here, right? You'll be able to now use the lemma, then you'll be able to use the induction hypothesis, and you should be able to finish it. It's only a couple lines. See if you can fill those in, and then we'll do that together. Right? Okay. I will see you on Friday. But if any of you have any homework questions or anything that you might need hints with, just let me know. Okay.